Hello and welcome to this EE514 short lecture video on the mathematics behind the LQR continuous time, infinite time optimal controller. This lecture video assumes that you are at least interested or have seen the motivation behind modeling the linear quadratic regulator cost function, and so we're going to skip over that part of the content. And what I want to focus on in this small lecture is the derivation and the proof behind why the full state feedback that we computed in previous lectures is the optimal control. So to that end, I want to prove a theorem that's in your textbook, and I want to walk through this theorem because it is a little bit out of place, I think. It's not particularly well motivated in the text, and so I want to give it a bit more of an explanation. And it's going to be a stepping stone to the goal of this video. Okay, so to set the stage, we're talking about a linear time invariant system, and we're going to say that its initial state is x0, and we're going to define the cost function of any control choice to be the integral over all time of the quadratic form x transpose qx, and remember these are time functions, plus the integral of u of t transpose r times u of t. And the restrictions that we're going to put on the q and r matrix are that q is positive or symmetric positive semi-definite, and that r is symmetric positive definite. Okay, so that's the typical LQR setup for infinite time. And so the theorem that I want to talk about right now says the following, is that if the control u star, which takes this form, stabilizes the system and results in this quantity being both minimized over all possible controls and that minimum value equal to 0. So we'll come back to that in a second. For some v function that looks like a quadratic form, then the u star that you started with is optimal. Optimal in the sense of it minimizes j of u over all possible control efforts u. Okay, so let's unpack this relatively long theorem statement. So first off, we have a quantity. And this is a quantity that's a function of u, because in the end, the state, or the trajectory, is a function of, well, it's a function of where we started, of the initial state, but then after that, it's a function of the control. Okay, so we get to steer the state, so these are x of t's, but truly those x of t's are also more explicitly functions of the control. So this is a quantity. It's a scalar quantity, I think, as well, right? This is a scalar, 1 by 1, 0, right? Because u transpose ru is a scalar. Add that to a scalar. And the v function itself is a scalar, so its time derivative is a scalar. All right, so we're doing a minimization over all possible functions u of this scalar valued quantity, v dot plus x transpose qx plus u transpose ru. And so if we start with a controller that looks like this, that is, it's a negative full state feedback controller, and that minimizes the quantity here underlined, and that minimum value is 0, then the u star that we started with actually minimizes the j, which is what we're actually after. Okay, so this is a bit of an end around, right? We're going to do some minimization on this function, and we're going to claim that that actually minimizes the thing that we want. All right, so why would that be true? Here's the proof. Well, if we take this statement, then we can rearrange that and put the x and the u terms on the right-hand side, and we get v dot equals the negative of these guys. And since this is a time derivative, then we can take the time integral of both sides of this equality, And the fundamental theorem of calculus says that'll be the v function at the final state minus the v function at the initial state. But if we also know that the control stabilizes the system, then the final state will be 0. And we know that if v has the form x transpose px, then v of 0 will be 0. So that means that this whole thing is 0. We don't quite know what v of x naught is, so we have to leave that alone. And the right-hand side of this integral is simply the integral of x transpose qx plus u transpose ru. And recall that this is our cost function. This is j evaluated at u star. Okay, so that'll become important. We drop the negatives, and this result says, so this cancels with this, this says that j of u star is equal to v of x0. All right, and that's pretty nice. The optimal cost is dictated by our, quote-unquote Lyapunov function at the initial state. And I think that's a little surprising. But we actually haven't gotten to the main claim of the theorem, and that is that this u star is optimal. Okay, so to prove that, we're going to go proceed, and this is what the book does as well, we're going to proceed by contradiction. So this is a proof technique that says, if I claim that something is true, if I show that the opposite of that can't be true, then I've shown that it has to be true. So, to wit, in this particular case, let's suppose that there's some different utility that produces a smaller cost. So this is my contradictory claim. Right? If that were true, then the theorem had to be false. If this is false, then the theorem has to be true. So let's take this new control law utility and say that plop it into this scalar valued function. So we're going to look at v dot evaluated at u tilde plus x transpose qx plus u tilde transpose ru tilde. However, we know from the theorem presumption, or from the theorem statement, that this quantity is no smaller than what happens when we plug in u star, right, because of this minimum statement. Okay, so if I evaluate it at any other u, like u tilde, I'm going to get not strictly greater than, but at least greater than or equal to what I would have gotten if I'd plugged in u star, which is 0, right, because of this part of the statement. All right, so that tells me that I can do the same trick now. I can say that v dot at u tilde is greater than or equal to these guys move to the other side. And I can again integrate with respect to time. And so that tells me that v as x goes to infinity minus v at x naught should be greater than or equal to the negative of the linear quadratic regulator cost at u tilde. If u tilde is going to produce a smaller cost, that means that u tilde also has to stabilize the system. Because if it didn't, then over infinite time, if the state never goes to 0, then we're going to accumulate an infinite cost. So this also has to go to 0 for the same argument that we had before. So this tells me that v of x0 is less than or equal to, because I multiply by -1, j of u tilde. But remember that we just proved, or we just derived, that this quantity, v of x0, is equal to the cost of u star. Okay, so we've just shown that if we assume u tilde produces a smaller cost, then it produces a greater than or equal to cost. So this is the contradiction. right? We assumed this thing, and then we derived the opposite thing. So maybe the alligator should be flipped around. This is equivalent to saying j of u tilde is greater than or equal to j of u star, which is the opposite of what we were supposed to show. All right, so this is the proof that a optimal control, you can show that it minimizes j, or it's equivalent to showing that it minimizes this function, and that minimum value is 0. And so that's the utility of that theorem, is that instead of trying to minimize the j, which is an integral of overall time, we can instead minimize this expression, which I'm just going to call f of u for no particular reason, right? Because we've just shown that if u minimizes this f function, then u minimizes the cost function, the j function, which is what we're actually after. Okay, so this is kind of an equivalent workaround. The utility of this is we can differentiate f, right? Because f is scalar valued, and with respect to u, and we can apply, unconstrained optimization theory, right? So this is the idea that the function with respect to u itself is a function, but I don't want to go into the weeds of variational calculus. What we're going to do is we're going to set this thing equal to 0, just like you would in Calculus 1, and try and determine the optimizing u that minimizes this function f. Okay, so let's get to it. We know, or we have assumed that v, number v of x, has the form x transpose px, and also recall that x dot equals ax plus bu. That's the land that we're living in here. So if I differentiate v with respect to time, chain rule tells me I get x dot px plus xp x dot, and the other two terms are carried down directly. And then what I'm going to do is I'm going to sub in for x dot. So this is my state evolution. This is my state evolution here. And the other two terms are carried down directly as well. And now I'm ready to differentiate with respect to u. This term has no u's in it. This term gives me a b transpose px. So that's where this guy comes from. This term has no u's in it, and so these two combine to give me this term. This term has no u's in it, so when you differentiate it goes away. And then we're going to do chain rule again to split this into two terms. Now recall that the v function is a quadratic form, and this u transpose ru is also a quadratic form. In particular, they both equal scalars when you do the multiplication out, and so when you differentiate them, they should be equal to their transposes, which is why I'm going to combine this into this term and this into this term to give me x transpose p times b plus, times 2, plus 2 u transpose r. All right, and so the first order necessary condition for a function to be optimized with respect to its independent variable is that the derivative should be 0. All right, so if we set this thing equal to 0 at the optimizing control, we get the 2's will cancel, and we get negative x transpose p b, and then if I multiply by r inverse, that gives me u transpose star, or the optimal u transposed. Of course, we don't want to write this with the transposes, so this is equivalent to saying that u star is equal to r inverse b transpose times p times x, where I've used a couple of facts here. First off, because r is positive definite, that means it's non-singular. So its inverse exists. Also, to go from this line to this line, I've capitalized on the fact that if R and P are symmetric, then they equal their transposes. And that's also true of R inverse. So R inverse. So R being symmetric implies that R inverse is also symmetric. All right, so that's why you don't see transposes on the R and the P down here. Forgot the negative. There we go. So there you have it. The control that optimizes the cost function, J, has the form of a full state feedback controller. So I'm going to often abbreviate this matrix K star. And it's the different K than you would get from your eigenvalue placement or your Ackermann algorithm, but it is nonetheless a full state feedback control. Now there is a second step to this procedure, and that is proving that this U, that this optimizing U is actually a minimizing U. So for that you would need the second order necessary conditions, and they would look something like partial 2f partial U squared. And just showing that indeed that this is a minimum rather than a maximum. Okay, so that's great. We start the problem with x dot equals ax plus bu, which means that we have b handed to us, and we have decided on x transpose qx plus u transpose ru as our cost function, which means that we have r in hand, which means check mark, question mark. Where's the p? How do we get the p? And that's the topic of the last slide in this lecture. To find the p, we need to solve an equation called the algebraic Riccati equation. So let's derive that now. So this is a result from last slide. This is our LQR optimal control. And I'm going to again refer to this thing, this R inverse B transpose P, as K star, just to remind us that it is a full state feedback controller. And if we implement that, then the dynamics of the system become A minus B K star times X. All right, so from the theorem on the second slide, we know that at the optimal control, this function, right, this is f of u star, is equal to 0. So let's take a quick side, and this term I've simplified over here on the left. So again, this is chain rule when time differentiating v, and then I am subbing in expressions for x dot that we had here into every x dot that we have in this line. Okay, so this line then produces this line, and that's all going to be subbed in for the v dot evaluated at u star. Okay, so these terms all come from this line, which all comes from v dot. And I factored out an x transpose from the left of every term, and I factored out an x from the right of every term, which is why the q is a little naked here, because its x transpose and x have gone to the outside. And then I've also subbed in the expression for u star into this expression, and so the r comes down here, and the x transpose and x are again factored away. Okay, so we know that this is a scalar valued function. It's a quadratic, right? It's x transpose on the left, x on the right, so it's a quadratic expression. And it's going to equal to 0, which is a scalar 0. But we need this to be true over all time, which means we need it to be true over all states, which means the only way that this line can be true over all states is if the middle thing itself is 0, right? If I can't rely on the x's to zero out this expression, then I have to rely on the bracketed term. And so that's where we get this line, is I've dropped the x's away, and I require that the bracketed term be an n by n 0 matrix. And the reason this line got so complicated is because I then expanded the k-stars. So this k-star transpose gives me this, and this k-star gives us this, and again this k-star produces this, and this k-star produces this. Now, let's remind ourselves that P is symmetric, so P transpose is equal to P. R is symmetric, so R inverse transpose is equal to R inverse. B, we don't have any symmetry about that, so B transpose, we gotta leave it alone. And here, we actually have an R and an R inverse multiplying each other, which gets us identity. And once you make these three simplifications, I think you'll see that this term is equal to this term is equal to the opposite of this term. So I've got two negatives and one positive, so I end up with one net negative. And then I've moved the q to the other side. And this is what's called the algebraic Riccati equation, or 2C's. Sometimes, and I think this will be important in a little bit, this is called the continuous time. Continuous, spelled correctly, time, algebraic Riccati equation, or if you're feeling cute, the care. So the P that gives us our optimal control is the same P that solves this expression. Everything else in this expression is known. A is known, B is known, R is known, Q is known. And the reason that I bring this up is because I want you to see the connection to Lyapunov, right? If we were to lose this term, this would be exactly the Lyapunov equation. So that's why I wanted to talk about Lyapunov stability and Lyapunov equations before we got to LQR control, because the spirit of Lyapunov lives here. We have to modify it because we're looking now for optimal control, not just stabilizing control. But the idea is that this is a direct descendant of Lyapunov. Great. Thanks for your time. I'll see you in class.